So now we are going to start chapter 25. In today's lecture, we are only going to cover the first part, talking about fluid balance. Our body is actually very high in the fluid composition. So between 45 to 75% of our body fluid is made out of body fluid, right? So we are going to say, why is that big range? There's a huge difference between your body is made out of 45% of fluid versus 75%, right? Well, that's because there's a couple of variables that's going to decide how much your body is made out of the body fluid, the percentage of your body fluid, right? If age is a big factor, so the older you are, the lower percent of the fluid you have, right? So basically, the babies have a really high percentage of the body fluid, but then the older you are, the lower the percentage of your body is made out of fluid. And then also your tissue composition, whether you have a high limb mass, percentage in your body, or versus, basically you have high percentage of adipose or skeleton muscle. Because adipose tissue in general has lower percentage of fluid, and skeletal muscle tissue has high percentage of body fluid, you should be able to fill up these blanks, right, yourself. So if I give you examples of, people, older people, young people, babies, that you should also be able to tell which one of them have a higher percentage, right, of body fluid. Next, well, in terms of what are we referring to about body fluid? Where is all those fluids located? There are actually a couple different places. First, we divide them into intracellular fluid versus extracellular fluid. If you remember in AMP1, when we talk about cells, right? The cells inside of the cell cytoplasm membrane there's the cytosol, right? So there's a lot of intercellular fluid inside of each of our cells. So if we look at the percentage, right, if we count all the fluid that's inside of the cells, right, that's what we mean by intracellular fluid. That's account for 2/3 of total fluid in our body, because our bodies, our tissues are made out of predominantly of cells, right? So that's where the bulk of the total fluid localized inside our cells. But then there's 1/3 that's localized to the outside of the cells. So we call that extracellular fluid, right? And then the extracellular fluid can be further divided into interstitial fluid versus the blood plasma, right? So interstitial fluid made out of 2/3 of the ECF, right? Extracellular fluid, and blood only accounts for 1/3 of ECF. And they're separated, right, by this capillary wall. So if you remember, well, what's the difference between the interstitial fluid and the blood plasma? The biggest difference is actually there's blood plasma have high protein content, right? Because we tend to keep the proteins in the blood. The interstitial fluid actually have very little, if any, protein in the interstitial fluid. So that's the protein content difference is the biggest difference between those two. Here's another look comparing the percentage of solids in different type of body fluid. Since we were talking about the interstitial fluid and blood plasma in the last slide, right, we would start here. You can see the different color of the column, actually the box is showing you the different type of the ions, right? Electrolyte. You can see they have very similar kind of percentage in terms of the ion, right? The electrolyte, the types of the electrolyte, and the percentage of the electrolyte in their composition, right? The biggest difference, just like we talk about, is the protein concentration, in the lack of protein in the interstitial fluid and the presence of protein in the blood plasma. That's the biggest difference. Well, because the the interstitial fluid doesn't have protein, you actually instead most that 10% of protein going to be actually become kind of split between the chloride ion, right, anion, and bicarbonate. So you have a higher percentage of chloride in the in the interstitial fluid than in the blood plasma, but no protein. So you kind of see the overall kind of pattern holds true. The electrolytes, right, are roughly the same kind of electrolytes are in the interstitial fluid and in the blood plasma. But if you then compare the ECF components, that's those two, to the SAF, you see the different colored box, right? Because we talk about different color of box indicate different type of ions. And you kind of immediately see the difference. Well, that's because SAF and ECF have very different composition in terms of the ion, right? The solutes. The predominant cations in the ECF is sodium, right? The predominant cations in the SAF is potassium. So you have mainly potassium in the cells and some magnesium, right? And the predominant anion in the SAF is a phosphate anion, right? But then in the in the ECF, right, extracellular compartment, the predominant anion is actually chloride anion and bicarbonate, right? So you can see the dramatic night and day in terms of the ion, right? The solute or electrolyte concentration composition and the composition. And that's actually going to be important. Knowing which type of the cations is the most important one, the highest dominant one in the SAF versus the ECF is critical for your understanding of the balance, the fluid and electrolyte balance we're going to talk about in this chapter. Well, here's another summary, right, of the main composition for the SAF and the ECF, right? So it's important for you to know that. Then next, since we today are going to mainly focus on the fluid balance, right, overall, and so let's look at some scenario, right? You are basically we're going to have basically the fluid movement we're talking about, mainly talking about the movement, right, between the three kind of compartment we just talked about, the blood plasma, the interstitial fluid, and the intracellular fluid. So there, the water predominantly is the water movement we're talking about, right? So because they are separated, right, by the capillary, vessel wall or the cytoplasm membrane, we know the ions there is going to be hard for them to move freely across those selective membranes, right? But then water, instead of them, because they're selective permeable, instead of the ions movement, we're going to have water movement, and that's the process by osmosis, right? When you have different osmotic pressure between different compartments, then you're going to have water movement. And let's look at two scenarios, right? Let's look at, if you drink a lot of water, right? You have fluid intake, and then your blood is going to become hypotonic compared to the SAF or even to the cells, right? Hypo meaning below the kind of tonicity of your surrounding tissue. And when you have hypotonic, so then you have water move out of your water move out your blood into the into the interstitial fluid, and then could be further moving into the cells if the difference is big, right? And when you're having, so that's the movement, the direction of the movement from the hypotonic place to the hypertonic space. And the same thing goes if you're, you're overheated and you're dehydrated, right? You are going to end up, when that's the case, the blood is hypertonic compared to the blood, the intracellular fluid become hypotonic, right? The direction again of the water movement is from the hypotonic space to the hypertonic space. Well, having said that, right, we know there's water movement going to be in our body if there's an imbalance in terms of the osmotic pressure or the solid concentration, right, between the different compartments within our body, right? So that's kind of setting out the tone. It's important for us to keep a fluid balance, right? So that we can make the movement, right? Use that movement of the direction of the water movement to our advantage and keeping our cells hydrated, right? Keeping our tissue hydrated, and so then we can function normally. And so that's essentially what we're trying to strike here, right? Have a fluid balance. When we're talking about balance, right, we're actually talking about the fluid intake needs to be equal to the fluid output, right? So that's what, when you achieve that, then we achieve the balance. So let's first look at, what are the forms of the fluid intake. The first is called performed water. Remember, you need to remember this term we use. So that basically means the water intake that we need to actually do something, right, to be able to get the water into our body. So that's through the mechanism of us drinking water, and it sometimes is, a fluid in the food. So it's drink and food. And so most of the water intake apparently is through performed water, but then some of the is actually from the metabolic water, and that happens in the mitochondria. If you still remember anything from AMP1, we were talking about the cellular respiration, because if we're metabolically you're breaking down, our energy molecule and try to get energy from them in the mitochondria, right? We are actually putting electrons onto the oxygen and to make water, and so that's that's called metabolic water we got from the metabolic chemical reactions, right, in our body. We didn't have to do anything. As long as our body are functioning, are making, energies for us to use, right? That's generating energy for us to use. That's the water comes as a side product from that reaction. But the super majority of that has to be from performed water. Then if you look at the water output, then there's the obligatory or the facultative water loss, right? So obligated means, right, they are way, it's out of our control, right? In terms of they are the water we're going to lose anyway, right? So it's from the breath we are taking, right? Every breath we we let out, that some we're going to lose some water in the expired air, in terms of they're kind of a little bit steam, moisture, right? Air we breathe out, we are constantly losing water through that. We're also losing water through sweat. We're also losing water through cutaneous transpiration. So that is the water losing from skin, not through sweat, but just skin. And we're losing also some water from feces every day, and the urine, that's the obligatory part component. That's the minimal volume of urine that we need to actually generate to be able to eliminate the metabolic waste, right, from our body. So that's called the minimum urine that we actually generate. Um, so that's called obligatory urine output. That's about half a liter, 500 ml. So all of those are called obligatory. So we kind of, those we're going to lose water, right, through those mechanisms. So the other component, we actually tends to lose more than, generate more than 500 ml urine, right? And if you remember, just we talk about, we are actually, in terms of the urine output, we usually generate between 1 to 2 liters each day. Why is that difference? Because the facultative urine output is depending on the hydration of our body, right? The more you drink, the more urine you're going to end up generate and use to keep your fluid balance. If you don't drink that much, right, you're slightly dehydrated, then you are not going to have a lot of facultative urine output, because you need to keep that water balance, right, fluid balance. So that is the part that controlled by the hormonal regulation at the kidney nephron. We're going to talk about what are they, right? So it's actually mainly by ADH, the one we also talk about at the beginning of the lecture, right? So you actually have to be aware of those categorization of the fluid intake and fluid output, right? So in addition to the obligatory and the facultative fluid output, you can also divide them into insensible or sensible. Sensible meaning we are aware of them, right? Insensible meaning we are don't really aware of the, we can't even sense, we're putting out those fluid. So different categorization you need to also be aware of. Another way to understand why we're keeping, what do we mean we need to keep the fluid balance, is you can think about it as a bucket, right? So as a bucket, what's going in is the food and drink, all the water input, and what's coming out, there are some things you can control. The regulated fluid output you can control in a sense by urine, facultative urine output, right? Anything that's beyond 500 ml, then you turn the faucet. But the other parts, the obligated part, you cannot control. They are the hose on the bucket. They're going to get out, no matter the fluid going to flow out, no matter what, right? The part you can control is the regulated fluid output here. Well, in the elderly, due to we talk about the lower fluid makeup, even a small loss in the water may result in an imbalance, such as hydration. Well, what if, you're this basket, if you take this basket, right? What if you're having too much water inside, or if you're, having too much fluid output, right? And that's going to result in fluid imbalance. Actually, fluid imbalance can occur either because of the fluid input and output it doesn't equal, or because of the abnormal distribution of the fluid, right? So there are 5 different conditions are all fluid imbalance. So volume depletion or volume excess, both of those 2 conditions happens, but without changing the osmolarity of the fluid, body fluid. So you have isotonic, excess of the fluid. So that will be the volume excess. If it's isotonic depletion, such as hemorrhage, right? Hemorrhage is losing blood, or vomit, diarrhea, all the hyposecretion of aldosterone. Aldosterone is, regulating both the sodium and water reabsorption. So if you have too much too little of that, you are going to lose a lot of the volume. If you have too much aldosterone, you're going to actually end up having too much of the volume, right? Get reabsorption of the salt and water, so are going to result in the volume excess. So those are the conditions without changing the osmolarity. But the next 2, dehydration and hypotonic hydration, right? Both those 2 are related to the changes in the osmolarity of your fluid. So that means, so for example, dehydration is probably the most the most often, the most frequent type of fluid imbalance, right? So that is because you're losing a lot of water, right? So then you are actually resulting in a hypertonic, just like the first diagram we saw, the hypertonic, of your blood. So then the water starts to shift, right? If the ECF becomes hypertonic, then the water is going to shift from the cells into the ECF compartment. Then you could have the dehydration of body cells. The hypotonic hydration or water intoxication is referring to then if you have, hypertonic or hypotonic in the ECF, right? If you drink too much water, but just the water, not the electrolyte, and your body fluid, your blood ECF, right, becomes hypotonic. So that could drive the water into the cells, because water is going to move from the hypotonic place to the hypertonic space, right? Then results in the swelling of the cells. Both those 2 conditions could be severe and could be lethal if not under control, right? So the last type of the fluid imbalance is edema, and that's because of the imbalance in the distribution of the fluid. So it's the fluid is sequestered in the compartment where it's not supposed to be. We actually have talked about edema, mentioned edema as the consequence of defective function of liver, defective function of heart, right? So this diagram here showing you the factors, right? Either you increase the formation of interstitial fluid by heart failure or faulty valves. Those are the things that defective in the cardiovascular system. You could end up increased formation of the interstitial fluid. Or you could be because of the decreased removal of interstitial fluid. That's often the case with defective in the lymphatic system. Right? The lymph return is impaired, or because of the liver problem, such as low blood protein level. So then there's less blood colloid osmotic pressure in the blood, so affect the water, the fluids reabsorption at the venous end of the capillary bed, right? So that's both those conditions, all of those conditions going to result in edema. In order for us to counter, right, the fluid imbalance, we need to have a way, to regulate the fluid balance, right? And in order for us to regulate fluid balance, we have to have a way to monitor whether our fluid balance is normal or not. And our body doesn't have a direct way to monitor the fluid balance, but indirectly, we're able to monitor the fluid balance by monitoring the blood volume, blood pressure, because those are all measuring the ECF, right? Blood is and blood plasma osmolarity. So essentially, they're all monitoring the ECF, volume, and the osmolarity. And so how do we carry out the regulation, right? So if we go back to the first diagram, we look at water intake, right? If we drink some water, right, we are going to end up with a bigger blood volume. A bigger blood volume, we know from the cardiovascular system, is going to result in higher blood pressure. So by monitoring the blood pressure and blood volume, we can actually have a sense of the fluid in us. And if we have the water, more water than the solids in our in the fluid intake, that's going to result in lower blood osmolarity, right? So by monitoring the blood osmolarity, then you can tell whether our fluid, whether we have more water than the solid, or whether they are about the same. To monitor the fluid output, right, we can also know by looking at the blood volume, right? If, let's say, you should be able to fill the blanks here yourself. If we have fluid output, right, that's going to result in what? Increase or decrease of the blood volume. That should be decrease of the blood volume, right? That should be opposite of this. And of course, if the decreased blood volume, that should result in lower blood pressure. That's actually one of the ways how do we modulate, right, blood pressure is by regulating the blood volume. And if we get more water output, right, than the solids, right, do we have higher blood osmolarity or lower blood osmolarity? Remember, this is fluid output we are talking about. So if you're losing more water than losing the solid, that's going to result in higher blood osmolarity. So everything is kind of opposite in the fluid output compared to the fluid intake. Well, then we have actually in our body, there's a thirst center that's actually in the hypothalamus and regulating the thirst center, regulating the fluid intake is actually a important function, right, for the hypothalamus. So what does this thirst center do? Well, it's actually help us, right, to stimulate, to kind of coordinate the water intake or the output, depending on the sensory kind of information, modulating the saliva secretion, right? Sensory input of the, also collecting information, for the blood osmolarity, right? Also detecting the blood pressure, right? All of those going to the thirst center, right? So if you have decreased saliva secretion, if you have increased osmolarity, right? And if you have decreased blood pressure, all of those stimuli is going to activate the thirst center. And so we're going to be aware we're thirsty, and then we're going to actually try to go drink some water, right? So you'll become consciously aware you're thirsty. So those are the stimuli to activate the thirst center. And how do you then turn off or inhibit the thirst center? Right? For anything, you need to have a switch on, have a switch off, right? So when we have actually normalized, right, the saliva secretion, or normalize the blood osmolarity, or normalize the blood pressure, all of those, opposite of those, going to turn off the thirst center. In addition to that, it's really clever. The stretched stomach wall, because that's a sense that you have taken food or drink, right? So that's where the water going to come from. And that's going to also inhibit the thirst center. So in addition to the nervous system control, that's the thirst center. Major hormones are also going to be involved in regulating the fluid output, especially the fluid output through kidney. Okay, we just talk about the urinary system, right? And that's by control the facultative output. And for major hormones, at least here, and you're probably going to be like, wait a minute, I know that those hormones are actually the same hormones we said in the cardiovascular system regulating blood pressure. That's exactly right. And you again have those three functions lumped together. They decrease urinary output, right? And then you have the single one, the natriuretic peptide increase urine output, right? So it's actually those are the same for involved in the blood pressure control exactly by at least part of their the way they are regulating blood pressure is by regulating urine output, thereby influencing the blood volume and therefore influencing the blood pressure. So Jose, our supplemental instructor, is going to have a session focusing on those 4 hormones, and to summarize that, and he has made a worksheet for you guys to really summarize all the related information about those hormones, and that's very helpful for you. I would suggest you to go to his session and to actually finish that worksheet. And it's not going to be important for this chapter but also for the final, right? Because you have to know how these 4 hormones work in the cardiovascular system but also in the urinary system. And we are going to mention them again during pregnancy. So, it's good go to his supplemental instructional session and work on those hormones there.